All right. Happy Friday. Welcome. Nice of you to make it. The only few that made it. So what I've decided, and I think the timing's going to be pretty good, is we're going to do quiz 2 next Friday. So quiz 2 will open next Friday, which is when? October 22nd. Okay. And for me, I liked how it went with the other quiz. So I was just going to do that again. So it'll be available during our class time, our regular Friday class time. But if you want to wait, then it'll be open for the entire weekend until Sunday night. So it's a 50-minute timed quiz again. Timed quiz, open from probably about from around noon on Friday. Feels reasonable. From noon, so 12 o'clock on Friday until Sunday at basically midnight, 11:59. Okay, and so what that means is that we're not going to meet on Friday next week, right? But you will be able to do the quiz if you want to use the class time to do that. That's great, and that's, it's kind of my way of kind of giving us a little Friday break, right? You guys are the only ones that are here, so I think everyone has other things going on Fridays anyways. So hopefully that works still. It worked out really well last time, I thought. So I'm just going to keep doing that. Okay, so quiz number 2. So the quizzes are strictly theoretical for now. Okay, and so the quiz number 2 will focus on chapters 4 and 5. I can't even remember what chapter 4 was on. Probability, I think. Oh, maybe I should move. I remembered this morning that I could do emojis, and so this changes everything. So here, how about that? Yeah. If I don't remember, how are you supposed to remember? But no, chapter 4 was on probabilities. So, and 5 is on clustering, and we'll talk more about clustering today. But quiz 2 will focus on chapters 4 and 5. Okay. Because I'm pretty sure quiz 1, I think, included chapter 3. Either way, I guess I'm committing here to what the quiz will be on. I'll have to check. I can't remember. I'm pretty sure I just wanted to do, yeah, I think I did. I wanted to do chapter 3 on quiz 1 and then 4 and 5 on quiz 2, and then kind of break it up a little bit more. Okay, and so only on lecture material, which so far, right, for chapter 4, there's really not any R that we're going to be doing, right? And for chapter 5, we're going to focus on the theoretical aspects, right? So what is clustering? What are some of the tools that we need? So we'll clear that up first. and then we'll be set for the quiz, and then I'll show you, how can we apply this stuff. So quiz number 2 will focus on chapters 4 and 5, only on lecture material, so no R. And because I can, hey. How about that? I know that's how you feel. No, it should probably be the little sweaty emoji with he's like smiling, but like like a little bit sweaty. It's that one, yeah. Yeah. It should probably be that one. I call it the few emoji, but I don't know if that's what it is. But anyways, I think it's funny. Yeah. Laughing, crying. Anyways, so yeah, so yeah, this is going to take up most of my time now that I can easily. I had found it before, but then I never really used it, although I love emojis, so I don't know why, but now I'll use them. I'll try not to as much, but it's hard. They're perfect. Okay, so yeah, so that means, right, and so just as a note, that means no, I guess, in class, or no meeting, no online, how do I say it? No Zoom meeting. That's what I want to say. No Zoom meeting on October 22nd. Okay, just as a heads up. Okay, because you can use it to do the quiz if you want to. You can use the time to do the quiz if you want to. No pressure. Or you can use it to study for the quiz and then do the quiz after. I don't know. Okay, so any questions about that? It's our second one, so should be okay, right? And it's all from the lecture material, so so you know what to study, and I think we'll be good. Okay, so if you do have a question, you can throw it in the chat or let me know. Otherwise, we'll keep going, and we're talking about clustering. So just in terms of some review, I should have reviewed before class. Now I can't remember. I was working on something else before this, and that always kind of messes with my brain. I shouldn't do that. Work on other things. The nerve. So in terms of a little bit of review, we talked about clustering. And so clustering, we have data and we want to create these groupings, these clusters, right? I'm trying to not use the same word. And so creating groups in our data, right? Or rather maybe finding groups, right? I'm going to replace it with finding groups in our data, because we're not really creating them. We're seeing if they exist, if there's some natural grouping going on in our data, right? And so that's what clustering is about. So how can we decide if there are groups, right? if we have distinct groups, well, we need to look at how close are our data points to each other, right? And so we need to start by thinking about, okay, well, how can I measure distances, right? And so clustering requires measuring distances. Clustering requires measuring distances. Then we talked about, for numerical data, we talked about the Euclidean distance, which is basically, if you think about 2 points on a plane, because that's the easiest way. Anything else in more than kind of 2-3 dimensions gets really, really hard to think about. In fact, for me, impossible. I don't know about you guys, but and so just to illustrate, we're going to focus on 2 dimensions, but it works the same in multiple dimensions. So clustering requires measuring distances. And so for quantitative data or quantitative / numerical data, we can have, we talked about the Euclidean distance, which is really just taking, 2 points like this, and then here is the Euclidean distance. There was the cute Manhattan distance, right? The Manhattan distance is, again, if we have 2 points here, then the Manhattan distance is this plus this. Maybe I don't need to write the same thing twice. In fact, I'm going to remove this because it should be obvious. Okay. Well, did we talk about any other distances? No, I think these are the main ones for numerical data or quantitative data, right? And so the Euclidean distance is just basically kind of the beeline as the crow flies, whereas the Manhattan distance, now you're walking around Manhattan, you somehow made your way to New York. Let's talk about that for a second. No. And now you want to get somewhere and you can see it. It's on a map and you just have to go straight across, but you can't do that, right? You can go just on the street sidewalk. It was blanking on the word. So you have to go around all the buildings, of course. Okay, and so then we introduced, okay, well, great. So those are some ways that we can measure distances for quantitative data. So for numerical data, what if we have categorical data, right? And so specifically categorical, but it has to be dummy variables. So 0, 1, which is binary, right? Binary or dummy variables. Zero, 1. Okay. So it gets a 1 if it's in the group and 0 if it's not in the group. Right. And so you could break up one categorical variable into multiple dummy variables. Yeah. And we said we introduced the matching distance. We talked about the matching distance, which we can't visualize anymore because there's no point in putting dummy variables on a plane. But the matching distance was, let me grab it here. the matching distance is, so what's tricky is the distance is the 1 minus the matching coefficient, okay? But the matching distance was this. Okay, so the matching distance between some points U and V, so some observations, right? We talked about, okay, in our data set, U would be one row, V would be another row. So then the distance is 1 minus the matching coefficient. And the matching coefficient was the number of variables with matching values over the total number of variables, which we reworked and said, okay, I can rewrite the matching distance as the number of variables with mismatching values over the total number of variables. Okay, so that's kind of the end of the review, and that's where we're going to pick up from last day. So it's really important, right, that we consider which variable is going to be a 1 in a categorical variable and which ones are going to be zeros. Okay? And so it will be really important. Sure, I'll say really in my notes. Why not? It will be really important to pick the appropriate group or the appropriate category, category to be represented by a 1 in our dummy variable. Why was that? Because the zeros aren't necessarily the same, right? So we lose information there, okay? And so I actually added, and that is all in here, right? But I'm actually gonna go down here a little bit. So for example, if our data was summarized like this, right, then age is quantitative, right? And so here age is quantitative, female 1 if the female, 0 if not. So that's a dummy variable. Income is the income in dollars, which is quantitative. Married 1 if married, 0 if not. That's a dummy variable. And children's the number of children, that's quantitative. Loan, they get a 1 if the customer has a car loan and 0 if not. So here, this is probably the most obvious or the first obvious situation where, okay, well, okay, I have a car loan, great. That means that I have a car, right? But I'm also paying it off. You can have a car, but not be paying it off, right? Maybe you've already paid it off. Or maybe you don't have a car. Notice how those two very, very different scenarios are lumped into the 0 group, right? And so they would have had to make a decision that, okay, the people that we want to kind of attack the most are those with the car loans. So those we extract explicitly, and then everyone else can be in a 0 group, right? So these are both dummy variables. So if we think about the loan, right? So a 0 can mean multiple things. It could mean I don't have a car, right? no car, therefore no loan. It can mean I've already paid it off, and therefore no loan, right? These two are considered the same, but they're very much not the same, right? These are considered the same, even though they're not at all the same. Even though they are not at all the same. Right? One, you have a car and you've paid it off. One, you have no car. Right? So same thing with the mortgage, right? Kind of less likely scenario. There aren't a ton of people who have paid off their mortgage. So that one's kind of more steady in my opinion, but still you're lumping people who haven't bought a home in with people who have bought a home and have paid it off, right? And so you want to be careful with that when you're interpreting your results. Okay. So let's see here. Okay, so when we say in the matching distance, when we talk about the number of variables with mismatching values, that's just going to be comparing, okay, do you have a 0 or do you have a 1? If that's the case, right, if we have mismatching values, then it would be counted towards the numerator, right? Whereas the denominator is just the total number of variables. Okay? So to kind of put a sort of a hamper on these zeros that don't necessarily mean the same thing, we introduce the Jacquard coefficient and the Jacquard distance. Okay? So hey, I guess I'll copy this whole thing, but I'm really interested in the bottom bit. Okay. So to avoid misstating similarity due to the absence of a feature, a similarity measured called Jaccards coefficient does not count matching 0 values and is computed as follows. Oh, we're at the edge of our seat here. I'll highlight this though. So Jaccards coefficient, which is not the distance, right? It's the coefficient, and then we take 1 minus the coefficient to find the distance. Okay, so the Jaccards coefficient, we'll start there, is the number of variables with matching 1 values for observations U and V. Okay. And then the total number over the total number of variables minus the number of variables with matching 0 values for observations U and V. So now we're kind of removing those matching zeros and saying, well, they're not, necessarily the same. Okay. And so then we can use that to calculate the distance. Uh-oh, gonna run out of room here. Crop top. There. So if we subtract the coefficient, Jacquard coefficient from 1, we get a distance measure for binary variables. Okay. And so what we have is the distance is going to be 1 minus the Jacquard coefficient, which is 1, which we can rewrite as a common denominator, which is a really huge one, right? The total number of variables minus the number of variables with matching zeros. And then I'm going to be subtracting the number of variables with matching ones. What's going on here? I feel like I'm missing a matching one here. It's just one. Oh, I see what happened. This isn't an equal sign. This is a minus. I need the few emoji. Okay, I'm going to highlight that because yeah, because what threw me off, right? I need a common denominator in order to subtract two fractions, right? And so really I'm just turning this one into the total number of variables minus the total number of variables with matching zeros over itself, right? And then, so then it just looks like I have one here, that's true, but then it's minus and I totally missed that. So what a relief. And then minus the number of variables with matching ones. So if we have the total number of variables, and maybe I should be over here, total number of variables minus the number of variables with matching zeros minus the number of variables with matching ones, how could I rewrite that? Well, I could rewrite it as the number of variables with mismatching values. Okay, over that common denominator of the total number of variables minus the total number of variables with matching zeros. Okay. So what we can do is we can have a look at just some situations here, right? And remember too, maybe I'll put it here and then I'll zoom in. You're not going to be computing these distances, okay? That's for software to do. But we need to understand the difference between using the matching distance versus using the Jacquard distance. Why would you use the Jacquard distance? Well, because I want to kind of stop the bleeding with calling these matching zeros the same. That's not necessarily true. Right, and so that's why we would use the Jacquard distance. So usually we end up using the Jacquard distance for that reason, right? The zeros aren't necessarily the same. Okay, but here, if we have an observation, so here we have 5 observations, right? And we're considering those 1, 2, 3, 4 binary variables, right? And so we can count how many females were in the 5 observations, how many were married, how many had a car loan, how many had a mortgage. Hey, only one of them. What do you think these zeros are? We'll never know. All we know is that they don't have a mortgage for whatever reason, right? We don't know. Hey, also weird. The one with a mortgage seems to be male. Okay, all right. So then what we can do is we can build up a matrix of the matching distances. So we can only deal with pairwise distances. So what happens is, of course, the distance between observation 1 and itself is 0. The distance between observation 2 and itself is 0. So like many matrices, we're only going to be concerned with one kind of triangle, right? And so that's why we don't even show these values here, because they would be replicated, right? The distance between 1 and 2 is the same as the distance between 2 and 1, right? And so we only need to look at one of these, okay? So what you could do is notice that we're only comparing pairwise, right? So we're doing pairwise comparisons, and we could go ahead and develop all these numbers. You could do it just for fun, just to get a handle on how to calculate these. They're here for you. But what you'll see is that some of these distances, once we look at the Jacquard distances, are going to be different, right? So they change slightly. Some of them won't, right? Because maybe there was no similar zeros, right? That's really the only difference here. So here, right, when I take into account that, okay, well, I actually don't really want to lump matching zeros into the same category, right, then the distance between these observation 1 with 3, 4, and 5, it increases, right? And so we can see here that typically it'll increase the distance if you have a lot of similar zeros, right? Nice. So those are those are just some of the ways that we can calculate distances. Okay? So now we need to talk about, okay, well, how can I create these clusters? Okay, so we talked about it, I introduced it last day, right? There are basically only 2 ways. So the first way is going to be, I have these kind of empty categories, and as I go through my observations, I put everyone in their categories where they belong, right? And then I might readjust a little bit, right? But in general, I start with some set number of categories, and I put everyone into their groups, right? And their most similar groups. The other option is everyone starts as their own group, right? And then you go around and you look around and you see, okay, where's someone that's similar to me? And then you join up and you make a group, and then you go out as a group and you try to find another group that looks like you. And then that's how you find these clusters, right? And so the first one is called K-means clustering. And the second one, where everyone starts as their own group and then you form bigger groups as you go, is called hierarchical or agglomerative, I think. Either way, you're kind of forming different, sorry, someone's at the door, so weird. But anyways, yeah. Okay, good. Sorry. Okay, threw me off. So let's see here. Focus. K-means clustering. Let's start there. Oh yeah, agglomerative. That was a word I had to look up how to say. So for K-means clustering, we're back to numerical observations. Okay, and so the reason is because we're going to be using means, and the mean only makes sense for numerical observations, right? And so here, I want to highlight that the mean, maybe I'll make this a little bit smaller to give myself some more room. We need numerical data for the mean to make sense. Okay. So K-means clustering is, we specify K clusters. Okay, so the analyst must specify the number of clusters K. So here in K-means clustering, the analyst must specify the number of clusters K. So that's where you start. Then given a value of K, the K-means algorithm, so you're not going to do this at all, right? Computer is going to do this for you, but we need to know which one to ask it to do. And there are benefits to both, right? And kind of depends on what you want. So given a value of K, the K-means algorithm begins by randomly assigning each observation to one of the K clusters. Okay, and so one key thing that might slip under the radar when you initially read this is, okay, so we decide we're going to have 3 clusters, K equals 3. Then it just takes each observation and randomly assigns it to one of those 3 clusters. Okay, so here I want to highlight that it randomly, because that might slip under the radar, right? So we start out and we randomly assign each observation to one of the K clusters. So after all observations have been assigned to a cluster, then we calculate what we call the centroid. So the centroid, so the cluster centroid are the means of the K-means clustering. Okay, so the centroid is just the average. However, we're going to have more than one variable, right? And so it's not just the average of one variable, it's kind of like a vector of the averages of all those variables, okay? So it gets a little bit weird, right? But if we think about just an X variable and a Y variable, then there's going to be some average of X and some average of Y, and we could plot that one point, right? And that would be the centroid. So the cluster centroid is calculated, okay? And then what we do is, so now each cluster has its own centroid, right? Let's say we said K equals 3, I had to count. K equals 3, right? And so now I've randomly assigned all my observations to one of these 3 clusters because I've decided I want 3. So then what happens is I calculate the centroid, which you can think of as just the mean, right? It's the mean of each variable in here that we're considering. So then I calculate the centroid for each of these. Then what I do is I rearrange the observations, right? Because now there's kind of like a centroid flag for each of these clusters. Right. And so now I say, okay, all observations just go to your closest centroid. How do you define what's closest? Well, we have those distance measures, right? So you would need to employ some sort of distance measure in order to decide which one is the closest, right? Depending on if you're using the Manhattan distance or the Euclidean distance, right? That might change which cluster to go to, right? So then, everyone's kind of regrouped to their closest centroid. So then we recalculate the centroid of each of these 3 groups. So now we have new centroids, okay? What happens then is, okay, people might need to rearrange, and I say people because I'm imagining like a sports field where people just kind of have to run to their closest clusters. It's not how it works, but it's fun to think about. Right, and so then things get rearranged and you go to your closest cluster and then you calculate the centroid again, and then it keeps going. So it's an algorithm, right? So it keeps going, it keeps iterating through that until there's no change, right? So until there's no change, it just repeats calculating, moving things around, recalculating the centroids, but eventually things will even out. And that will be your cluster. So the algorithm repeats this process, calculate the cluster centroid, assign each observation to the cluster with the nearest centroid until there's no change in the cluster. Or if you don't want it to run forever, right, a specified maximum number of iterations is reached. Highlight that. Okay, good. So that's K-means clustering, right? And so usually, and here, with the closest centroid, and we do have, so we typically use the Euclidean distance, which is just kind of the straight across distance. right? But we have other distances. So the default is going to be the Euclidean distance. Okay. A lot of information in that blurb. So here, let's talk about kind of some of the problems here. It's not a problem. It's just, it makes it hard, especially when you're just starting with this stuff. Okay, and so cluster analysis, there's no explicit measure of accuracy. Okay, so the notion of a good clustering is entirely up to the analyst, right? What level of kind of similarity do you need to have within your clusters? That's up to you, okay? We can talk about the strength of a cluster by comparing the average distance. So there it is again, the distance. In this case, the default is going to be the Euclidean distance, but you could compare different distances, right? And so we measure the strength of a cluster by comparing the average distance between observations within the same cluster, right? So basically, how tight knit are these people in this group from this the people in this group, right? And how far away are these clusters from each other, right? If you have two groups and they're kind of spread out like this and they're very close, well, there's nothing to say that that shouldn't just be one big group, right? And so as a rule of thumb, the ratio of the average between cluster distance to the average within cluster distance should exceed 1, right? It should be greater than 1 for useful clusters, okay? And so what can happen is you might have really big outliers in some of those clusters that kind of pull clusters together or potentially pull them apart, right? And so then what happens is you might find better clusters if you kind of hold them out for a little bit and kind of deal with those strong clusters on their own, and then continue the clustering process with just the remaining observations. So you kind of hold back these outliers so that they don't affect the clustering. And then you can maybe put them in their own cluster or put them in the most appropriate cluster. Okay. Often, you'll know just from experience or from a colleague or from your boss how many clusters you should be going for. How many clusters should you start with? But it's not that hard to just run through a couple scenarios and see what benefit there would be from having maybe 3 clusters versus 4 clusters. So that's what I want to just show you here, is that we're just going to compare what. All right. So if the number, oh, it's catching up here. If the number of clusters is not clearly established, either by context or just kind of from prior knowledge, right? The Kmeans clustering algorithm can be repeated for several values of K to identify promising values. We do that often, right? If you've done any sort of regression analysis, then, you know, we do, and not just linear regression, but multivariate. Then what we do is we put all the variables in and see if we get anything, and then we kind of tweak our model and we make adjustments and we pull variables out that are contributing, maybe put some new ones back in, look at different combinations. And so we do that a lot in statistics, right? Especially, and I mean, data science is just statistics pretty much. With a business component. But Emily, isn't there econometrics Yeah, it's existed for a long time. So yeah, econometrics is just financial statistics, right? So anyways, if you're deciding how many clusters should I have, you don't have to pick one and stick with it. You can try a couple of different clusters and you can see what the benefit would be to maybe using a few more clusters or a couple fewer clusters. In general, you don't want to have too many clusters because it becomes too kind of not very informative, right? But if you have 3 or 4 clusters, that's usually a good place to start. It totally depends on, you know, how you're trying to segment your observations. And so a common approach to quickly compare the effect of K is to consider its impact on the total sum of the squared deviations from the observations to their assigned cluster centroid. That's basically talking about the variance or the standard deviation, right? How far is each observation from its cluster centroid? That's one way that we could kind of analyze how far things are. And so what we could do, instead of reading this to you, I'm just going to talk about it because there's a graphic, but it's there if you need it. But instead, we're going to talk about this graphic, and man, time flies when you're having fun. Clusters. Okay, so I'll talk about this and then I'll leave hierarchical clustering for next day. Okay, so here we're considering a few different options. In fact, 1 cluster, 2 clusters, 3 clusters, 4 clusters, 5 clusters, 6 clusters. Would you ever do 1 cluster? No, right? But it's a good starting point, right? 1 cluster is basically everyone's in one group. So that's basically the same as, you know, if you didn't have any clustering at all, okay? So basically, how far apart is everyone in the data here? So this is kind of your worst case scenario is 1 cluster. So then we're trying to see, okay, what benefit can I get out of clustering, right? So if I jump to 2 clusters, now the sum of the within sums of squares is just a measurement of how different things are within the cluster or within each cluster. So now, right, if we started roughly at 60 at 1 cluster, that's worst case scenario. So then when I jump to 2 clusters, all of a sudden I'm at basically 25-ish, okay? 60 minus 25 is 35. So that's why this one is at 35. Okay, you can kind of ignore the red one for now and just focus on this blue one. So if I have 2 clusters, then the differences within the clusters reduces drastically, right? From about 60 to 25. So then if I increase it to 3 clusters, then they're even more similar, right? Which is what we would expect, right? We expect each cluster to become more similar as we break things up, right? And we allow them to kind of be in more groups. So here we see that, okay, I have now kind of a distance of 15 within each cluster. But then when I go to 4 clusters, maybe it jumps down to 10. So now I'm not seeing that benefit anymore, right? So depending on if you maybe need 4 clusters or 5 clusters or more, then of course you would have to do that. But the most benefit that we see is here at 3 clusters. Okay. So this is kind of the most benefit. And now I'm completely out of time. So I'll stop here and I'll stop the recording. But if you have any questions, let me know. Otherwise, we'll keep going through this stuff on Monday. All right. And I hope you have a great weekend. I'll see you later.